All right. So jumping into now, how do I do this ANOVA that we've talked about all the theory? So all of the assumptions still apply, so I still have to check for accuracy, missing, and outliers. Right? If they're missing any data, you're going to have to exclude them because it's going to be a large % of their data. Normality, so if we have at least 30 people, that would be okay. Linearity is especially important because this is still the linear model. Homogeneity, but now we're going to talk about Levene's. So we haven't talked about Levene's on how to calculate that, so we're going to add that. And homoscedasticity. So it's still a form of regression, so you still have to check for that. So this is your normal data screening, but now we're going to plus Levene's to it. So how do I do that? Levene's is in the CAR library. I am not sure if you guys have CAR installed yet or not.
I think we did that first class or something.
Yeah, I think I thought SKU was in CAR, but it's not. It's in Moments. So you need CAR. Okay. So the code for it is Levene test with a capital T. This is the chapter 10, 11, whatever chapter we're on, R code that I uploaded. And it's the exact same format, you'll notice, as the t-test. So Y is tilde X. So we're going to use the data that we have, tell it what data set it is. And the only thing that's different is center equals mean. We're using the mean as our model, so we want to center based on those means. You could also do median. So this will modify Levene's test for a different type of model if you were doing medians or counts. We're going to do mean because that's what we're doing. Let me open that code. Okay. Oh, I didn't add power. Okay, at some point I'll have to add power. I totally forgot to the notes. Okay. So the first thing I have in here is I loaded this up through Mimisk because I like that one a little better, and loaded the data set. So a quick reminder on how to work with SPSS files. You can use Mimisk or Foreign. I like Mimisk a little better. So I'm going to set my working directory to where the file is saved. So wherever you're saving the Viagra data set today, that's where you need to set your working directory. So you can run lines 2, 4, and 5, and it'll work. Hopefully. We won't have any issues.
That's not going to work.
Whoop, whoop.
You have to install all Mimics.
Oh, right. Thank you. I'm on the school computer.
Oh, you need to change. You need to set the working directory.
So set the working directory to where that Viagra data file is stored, and then you'll be able to run 4 and 5.
Like I know I'm not, so I don't have to do this because I switched over here. I just
Could not find as... Oh. Once you install the package, be sure to load the library.
How do you get that
This is my
working,
file.
the set working directory window to pop up?
And
Okay, so do session, set working directory, choose directory, and then that's where you can pick it.
easier than
If you save the .r code to the same place the file is saved, you can do to source file location. So quick practice, can we get SPSS files imported? Mimisk better. Okay, so next step, let's make sure CAR loads. Okay. It will give you a warning that it's hiding something from you. That's fine. It's because I think it's because they have both packages have the same name of something. I think. Not entirely sure. So Levene's test here. So Levene test with a capital T. I've got libido is dose, right? Because dose is our IV variable that's categorical, so it pulled it in as a factor. Libido is my DV. So remember it's DV tilde IV. The person column is just a participant ID number, so I'm not going to use that. Data equals the data set, and center equals mean. So let's run that bad boy, see what happens. And then I took a picture of it so I could blow it up. So the output you should get is it should say Levene's test for homogeneity and variance. And then it gives you a very simple table. It's actually just like part of this table. Okay. So instead of running these on means, it tests that the variances are the same between groups. Okay. So it tells you that the degrees of freedom are 2 and 12, which is the same degrees of freedom for the F test. It tells you what that ratio is, and then P. So really you want to look here at P. Okay, so the probability of it being greater than the null. So what we're looking for is the p-value significant? But remember, this is data screening still. So 0, 0, 1, less than that would be bad. So if you get 3 zeros or less, it would be significant and you'd have problems. And so I know you guys don't love looking at the residual scatter plot, so here's a cut and dry number for you. Okay. So less than 0, 0, 1 is bad. That's my new kids on the block rule. Remember, so 0, 0, 0 is bad. And because remember, this is still part of data screening, so it's still an assumption. Okay. So ANOVA, though, is called a robust test. I love this term because it makes me laugh because it just reminds me of boobs. I don't know why, but it does. So it's a robust test because I think that's the word people use sometimes. But what robustness means in this case is that it'll still give you an accurate result even if your assumptions are kind of bent. Okay. So if you bend the assumptions a little bit, let's say it is significant, ANOVA still tends to give you an accurate number. You can still trust the p-values that it's giving you. And that is true when groups are equal, so sample sizes are equal in each group. ANOVA tends to be less robust when sample sizes are very lopsided, and when sample sizes are sufficiently large. So that's the central limit theorem. Okay. So ANOVA is pretty robust to violations of assumptions, especially normality with enough people, and then outliers become a problem, a bigger issue. Okay, so through all of this, we're mostly going to say outliers are the bigger issue because they skew variance and the mean so much. So if Levine's test is significant, it's not usually time to panic. And we'll talk about there's a simple way to run a correction for Levine's for a one-way test. Okay. Oh, that's something else I haven't added. Make myself a list here. Okay, so how do I run the ANOVA itself? It's the AOV function for analysis of variance. There are probably 10 different packages that do ANOVAs. So there are lots of ways to do ANOVAs. I'm just going to show you this one. But we're going to save the output because we're going to use that output in multiple ways. So you're going to want to save it instead of just printing it out to the screen. Okay. So I'm just going to call it output. So it's the same format. Look how nice learning this format is. It's going to be repeated throughout the entire lecture. But y is approximately x. Data is what data set is it? Okay. So going back to R here. So the AOV function, I got libido is approximate dose, data is data set. So that's the exact same thing you see here in Levine's. Okay. ANOVA tests if there are differences in means, Levine's tests if there are differences in variances. Okay. All right, so let's run line 12. And then what you'll see is you get this output. It's a list of all this stuff. Like there's so much stuff in here. And so by saving it, it allows us to only pull out the things we're interested in, rather than looking at all this stuff. So the summary function, remember summary works on data sets and on lists, and so this will give you the basic, this table. So run that summary function, 13, and it will give me the summary table, that's what it's called. That was an unintentional match, but this has always been called a summary table. So it gives me dose, which is my model, and then the residuals, and it doesn't give me total because they assume you can add yourself, and then does all the division and stuff for you. So our F statistic is 5.12, and then there's P. So we said we needed 374 to be less than 0.05, so we knew we were less than 0.05. So what's the exact p-value? 0.02. So I would say this is significant, but just in case you aren't sure, it does do the little stars for you, which is nice because SPSS doesn't do that. And it tells you in the code down here just says how significant. So less than 0.05 gets 1 star, less than 0.01 gets 2, 0.01 gets 3. Okay. So it does star it for you. It will give you scientific notation to hang on to that options code we talked about last week in case you want to turn off scientific notation. Okay. So if the numbers get very large, it'll start doing SciPen. All right, so what do I look for in this table? Mostly you're going to look for the p-value. Is it less than 0.05? So does it have a star next to it? So it is significant. Yay! So what does that mean? Well, it means one of the means is different somewhere. Great, helpful. Right? Which mean? So we're going to get into post-hoc tests. But first let's do effect size. Oh, no, lies. First let's do what do you do if Levine's is significant, and then effect size. So if Levine's test was significant, or the homogeneity test in your scatter plot looks bad, what can I do? Well, the simple solution is a Welch correction. That corrects the differences in variance just like in the t-test. Remember, it was the Welch t-test as well. There are actually several different ways to correct, but one of the simplest ones is Welch. And all you're going to do is change AOV to one-way.test. So this is one of the things that I hadn't really explained. What do you mean one way? So ANOVAs, especially when we get to multiple IVs, are often described by the number of IVs they have. So a one-way test has one IV. Let's try that again. One IV. There we go. A two-way test has two IVs. A three-way has three IVs. Yeah, you get the idea. So anytime you hear something way, they're telling you how many IVs there are. I think this nomenclature is particularly poor because it isn't very descriptive. So when we get into two-way ANOVAs, we'll talk about the better way to describe them. But I don't want to confuse you right now. So anytime you see a one-way ANOVA, what they mean is there's one IV. It could be one way between subjects or one way repeated measures. So one way doesn't tell you the type of variables they have, it just tells you that there's one IV. So that's what this one-way code means. So one-way.test instead of t.test. On this one, you don't want to save it because the summary function doesn't work the same. That would be beautiful because then everything would be nice and the same every single time, but it doesn't do what I thought it would do. So just run it with no saving, and that is line 17. And it will give you a different look. So instead of giving it to you in summary format, it gives you just all the numbers you need to write it up in APA style. Okay. So check out what it does. So we talked about the Welch correction on T corrected the degrees of freedom, right? So it would change the degrees of freedom to this weird partial number, which changes your cutoff score, which then affects your p-value. Same thing. So it changes DF for residuals. Okay. So it's not significant if we do a correction. Okay. But Levine's test wasn't a problem. Don't want to use the word significant. So I wouldn't run this, but this is how. Okay. So throughout the semester, I'm going to try to show you, like, if the assumptions are broken, here's a simple fix, or go find somebody who knows non-parametrics because you can't fix that problem. Okay. So you would run a Welch correction. All right. So how would I write all this up? So listing T, we did T degrees of freedom, right, equals the T value, and then P, and then do exact P value. And then we added Cohen's D on the end, or G. Now we're going to do F. Remember, F is still in italics because it's a letter. Any letters in statistics are in italics. So it's degrees of freedom model, comma, degrees of freedom residual, or numerator, comma, denominator. Okay, these two in order. So we never use total. Oops, here. So I don't know why they talk about totals, but it's a thing. Equals the F value. P equals P value. So now you just have to stick both degrees of freedom in the parentheses. Also have eta squared on here. So let's talk about eta. Because it's effect size party. Right. So with ANOVA, there are actually multiple effect sizes. Two main paths. Generally, there's one for the omnibus test, the F statistic, and then there's ones for the follow-up test. And that's where it's t-test, so you just do Cohen's d again. But when we're talking about the overall test, there's several that you could list. And this is my joke about you can tell when people learn statistics or whose lab they were in by which one they use. Because most people use eta, so that's this little n here, so eta squared. R squared and eta squared are literally the same formula, so I do not know why we have two different labels for it, but we do. And then the little w is omega squared. I don't feel like I see that very often, but I know you're going to do it next semester. So I'm trying to get you prepared for Mitchell will want that, because old and new. I learned omega squared a million years ago, and my professor was like, well, I learned this at Brown, and all this stuff, and then she was like, but nobody uses it, so we're not going to do it. And I was like, why did I just learn this? But if somebody asks you for omega, you will know how to calculate it, like next semester.
Will we continue using R next semester?
R, I hope. Yeah, I mean the assignments and stuff that he has you do are often more theoretical than calculating, but you'll also have the same help desk person, so she can help you if he needs it in SPSS, but he knows that we're doing this in R. I warned him. So let's talk about R squared and eta squared. So the interpretation of these, so when we talked about D, we were talking about how different are the means. So it was the number of standard deviations, difference between the two means. But now that we have three means, we can't do that anymore. So it's the proportion of variability accounted for by an effect, which sounds like a bunch of random words, until you realize that the formula is the amount of model variance to total variance. So it's how much of the variance is the model over the total. Okay, so how much variance is accounted for by IV? Okay, so this is when I have 3 plus means. So it's how much good variance is there. The small, medium, and large criteria really are different in different places. I've seen this one, and then I've seen the one that I tend to use a little more as 0.01, 0.09, and 0.25. They're both okay. So we'll go with 0.01, 0.06, 0.15. The ones I'm used to doing are little r squared. But for some reason, r squared has slightly different ones. Shrug. Okay. So these are just guidelines. So think about this for a second. 6% of the variance being due to the model out of the total is medium. And so that is good for us because we're dealing with people, and people are weird, and they do weird things, and they fall asleep in your experiment, that sort of thing. So a medium effect is 6% of the total. That means you're talking about 6% compared to error. The other 94% is error. And so a small effect is 0.01, so only 1% of the variance is due to your variables. Since we're talking about variance and proportions of variance, it can only be positive, and it ranges from 0 to 1. Right, so if you get something over 1, you have mathed incorrectly. So it's the amount of variance accounted for by your model. So why are there two different formulas? I don't know. So most people tend to list r squared with regression and eta squared with ANOVA. Make that a little bigger. They're literally the same formula. So I don't know if that's just like nomenclature, like, oh, it's eta, it's ANOVA, oh, it's r squared, it's regression, but they are exactly the same. So pick a symbol that you like. R is easier to type than finding the little eta symbol. But if someone tells you, well, why don't you do eta? You can be like, listen, those are mathematically the same. Why are we still trucking with these? I think the reason is that SPSS, if you run an ANOVA, it tells you it's eta. If you run a regression, it tells you it's r. And I really think that's the reason why, because they're the exact same formula. So it's sum of squares model over sum of squares total. So we just have to add up model plus residual. So you could like math that out. So r equals blah. Or you can use the summary.lm function, and it will give it to you right there. Yay. Okay, so that's why we're saving it, because we can use it again here in a minute. So if I look, that is line 20. So summary.lm will give you the output from AOV as if you ran it as a regression. Okay. So we could, instead of using AOV, run LM, y is approximately x, and get this output. So AOV is a special function that gives you the output in this format. L is the exact same math as LM, which we've used a couple times. but won't give you this format. So the LN format gives you the more traditional regression style, where it'll give you the coefficients down here. Okay. But the cool thing about that is it gives you multiple R squared right here. So you don't have to math. Yay. So the R squared for our made up data is 46%. Generally, if you get R squares that big, I'm like, okay, what'd you do wrong? How did you get a number that big? Okay. When it's not made up data. Don't use adjusted. There are a lot of problems with that number. So just use multiple R squared. Okay. Easy enough? Yeah, summary.ln. Okay. So the issue now becomes omega. Okay, so what is omega? It's a correction on R squared, A squared. Okay. So we talked about D has a correction G. Omega is the correction for R and eta. And so it's supposed to be an estimate of the population. So it's kind of like how we talk about standard deviation. Well, that's too big. Let's use standard error. It's kind of like that. So it's going to estimate the population effect size. And it will always be smaller because it adds a correction. And this is probably the simplest math that we'll see when we talk about omega. The math for repeated measures omega is just, ugh. Pretty sure in one of the editions of the Andy field, he's like, you don't want to know. I think is what it says. It's really unpleasant. So what are all these numbers? So it's sum of squares model, so SSM, minus degrees of freedom model, times this time mean square residual, this number. So don't do sum of squares residual, or you'll get a negative number. Okay, so if you get a negative number, in theory, if you get a negative number and it's really tiny, omega is 0. And f will normally be very small. But if your f is significant and you get a negative number, you've done what I did and did the wrong numbers. Okay. So sum of squares model minus df times mean square residual divided by sum of squares total plus, again, mean square residual. Okay. So that's the tricky part, making sure that these are mean square and these are sum of squares. There is no plugin for that I have found. If you find one, let me know. Okay. I have no idea what happened. Oh, I think I was cutting and pasted. That little A thing in there should just be a minus. So I plugged in the formula. I just put in all the numbers that I got from the AOV output. Okay. So to get this, I would rerun my summary output to look at all of these. And this is where I got the numbers from. And then I mathed all that. So omega squared is 35%. So it will always be smaller. Sometimes only a little, but it will always be smaller. Because that's the point. It's a better estimate of the effect size in the population. We tend to overestimate with samples. So I'm talking 46% to 35%. That's kind of a sizable jump, but they're both large effect sizes. So that is how you do a one-way between subjects. So that formula only works for this particular design. Okay, so it's for one IV with between subjects variables. Okay. And when we get to the other ones, I have sort of a table of all of them together. We are trying to make the math on this happen for Moat, but the guy who does this stuff is more behind than I am, if that's possible. So, okay. So there's math. Okay, questions on that? So you could use my layout here. Just make sure you're filling in the right numbers. Okay. And to get total, I just added the two sum of squares together. Okay. Or you can use a calculator if you like calculators better, but remember that R is a calculator. So, and it knows, please excuse my dear Aunt Sally, because I don't remember it. Okay, questions on any of that? We're going to real quick add a slide about power, because I had a brain fart and I forgot. And I will upload these notes here in a second. So let's pull up G-power. And I bet that I still don't have it on my computer, because of course not. Why would I be so lucky? Wait. Maybe it's just hidden on the desktop. No. So anyway, we're going to pull up power, talk about how to do power for a one-way design. So I'm sorry you guys have to wait. Really, no questions so far. One-ways are easy to run. Yeah, it's the post-hocs. They're not hard. They're actually easy to run. Thank God. Last year was a disaster. I think Rachel's exact comments were mostly because I thought they were awful. Like she didn't want to do them, not because they were impossible, just she just didn't remember not liking it. I think was her exact words. I'm like, then we wouldn't be doing anything. Yeah. All right. So did I get it installed? There it is. Okay. So G-Power for ANOVAs. So the test family is now F for F test. And so that will change all of the options under statistical test. Okay, so I got an F test. And then under statistical test, that's fixed effects omnibus one way. Okay. So fixed effects omnibus one way, which really should say between subjects, one IV. And this is if you want to calculate the power for the entire study. Right? You don't want to calculate the power. You can calculate power for just one little piece, like one post-hoc test, but then you would be talking about T. So if I want to do just this, the whole study altogether. Okay, so fixed effects omnibus one way. Still leaving it as a priori. But you'll see this little effect size F here. That's Cohen's F. So if you hover over it, it'll show you small, medium, and large for Cohen's F. That is not eta, so don't put eta there, or R squared. That's a different formula altogether. But if you hit determine, it'll pop up in a box where you can type in the means for each group, or if you look at the little drop down here, effect size from variance, okay, and that'll give you the option to type in partial. What they have is partial eta squared, but eta. Okay. So there are lots of ways to enter the effect size here, but the easiest one is eta. Okay. So if I wasn't sure, I could estimate 0.01 or 0.06. But we have an exact number, so let's do 0.46, because that was the one we did. Calculate and transfer to main, so that will translate that into F. Okay. So that's the tricky part. It's not Cohen's D. And it's not automatically the number we would normally use. A lot of people use F. Psychology didn't really take it on, which is sort of interesting, because it's the same guy who did D, which we've all adopted, so I'm not sure why F hasn't caught on, but instead we're going to do eta. Alpha probability is still 0.05, power is 0.8. A number of groups is how many levels, so we've got 3. And then let's see, how many people did we need? We had 15, and it told us, oh, magic, that we needed 15. It was unintentional. So it'll give you numerator DF, denominator DF. So numerator DF is levels minus 1. Denominator DF is like, it's assuming equal sample sizes because you have the most power with equal sample sizes. So it tells you need 15 people. So 5 people in each group. And I'll add that to the PowerPoint slides and upload those for you. Totally brain farted out on that part. So I have 15 people and I needed 15 people. Magic. Questions on G-power or effect size? No, not yet. Not until you try it on your own, I'm sure. Yep. Okay. So let's do post-hoc tests. And I don't think I'll finish, but it won't be super long. So why do I have to do some sort of follow-up test? Sometimes they're called follow-up tests, sometimes they're called post-hoc tests. Follow-up test is more appropriate word to talk about all of them. Post-hoc is a specific type. Okay, but why? So we have, at the moment, we know that the test is significant and that something happened, but it doesn't tell us who did it, basically. So back to our bad Sherlock Holmes example. Something happened. This is the what happened. So where exactly did things turn out significant? So I don't know which group is different from which other group, And so I'm going to have to do additional tests. So we're going to run t-tests. And so I get asked this a lot. Why not just nix the ANOVA? We just don't. So we're going to figure out where those differences actually existed. Okay. A lot of people talk about ANOVA as the omnibus protection test. So you didn't run a whole bunch of t-tests if there were really no differences overall. So the first thing is something happening? And then it becomes what happened. This is a big argument whether or not you need the ANOVA, but traditionally people run ANOVA first. So there are a couple options to how do I find out which group is different. We could just do multiple t-tests, and we talked about earlier why that's a bad idea. So with no correction, no fix, that increases type 1 error rate, and you've wasted your time running the ANOVA. You could do orthogonal contrast and comparisons. Those are hypothesis-driven, so they're planned before the experiment in a perfect world. And those are generally things when you're like, okay, I'm going to take the control group and compare it to all the experimental groups, and then I'm just going to compare the 2 experimental groups. So I don't want to compare everything to every other thing. I want to do just these 2. So it's like I could do these 10, I'm just doing these 2. And you have a good reason why. And on those, since they're hypothesis-driven, most people don't do a correction. I'll get into what that means in a second. And that is what I have nixed from this semester because all the headaches. If anyone ever suggests that you should do that, the book does talk about them. Post-hoc tests, which is what most people do, are not planned. Or they might be that you plan to do it that way. So they're sometimes called a posteriori tests or posterior afterwards. I kind of went, let's see what happened. And this is where I compare everything to every other thing. Okay, so every pairwise comparison. And generally people are interested in all of these groups for a reason. So they want to know, how is this group different from every other group? So why would I limit myself to only these 2? And that's because you have to correct those. Okay, so orthogonal contrasts don't require correction. Post-hoc tests do. So we're going to correct for the fact that we're doing every possible combination. Okay. And this is really driven from a math standpoint. So orthogonal contrast, each one only uses the variance once. So if you use the variance for this contrast, you can't use it again. So you keep divvying up the variance, like we did model and residual, and then we break up model even more. So you can't use the variance more than once. Post-hoc tests use the variance over and over again. So it's kind of like you keep eating the same cookie, if that's possible. So I have to correct for the fact that I'm eating the same cookie multiple times. Okay. There's also trend analysis. So we're going to do the last 2. Trend analysis is for when you have groups, but you're really actually interested in it being linear. So it's kind of like ANOVA and then a regression. So some people say just run the regression, but trend analysis will also allow you to see if it's curvilinear. So if your ANOVA is non-significant, it might be because it's making a U shape and everything just kind of washes out. So trend analysis is really helpful for detecting curvilinear effects. All right, so we're going to do mostly post-hoc, and we're going to do 4 of them. And this is when you take every mean compared to every other mean. So because they're not planned, this is termed loosely, and we're running every possible combination, we're going to have to correct. So one of the big things I want you to get is that the post-hoc test is normally T or F. Okay. So the test itself is not Tukey. That's one of the examples. Or S and K, we're also going to do Scheffé and Bonferroni. So the test is a t-test. The correction is the Bonferroni, Tukey, or Scheffé. So Tukey isn't a test. It's a correction on the test. Does that make sense to people? Yes? So we're going to run a bunch of t-tests, which I told you shouldn't do, but then we're going to correct those t-tests. Why are we correcting? Because if you run a bunch of t-tests, type 1 error problem. So we're looping back to where we started at the beginning of class. Okay. So we're going to run a bunch of t-tests and then correct them. Okay. No correction would be bad, but I'm going to just show you how these corrections work by comparing it to not doing one. Okay. And this is that other Word doc that I uploaded, the comparison chart. Right? We're going to make that on the board. All right, we're back. So for all the post-hocs, it's a T test, except for CHEFE. Sorry, CHEFE is an F test, but then it gives you T. I'm not entirely sure about that output, but in theory, CHEFE is an F test. And it's going to tell me if those means are different. So we're going to line them up 2 by 2. This is back to Noah's Ark. See, are you different than you? Are you different than you? And let's see what's significant. Sometimes you will see this. This is how it's written in R. It's called the LSD. Just makes me laugh. Okay. There's also one called Fisher-Hader, which really makes all the IOs laugh because Fisher is a professor in our department. Well, I couldn't figure out how to make Fisher-Hader work without 16 lines of code, so not Fisher-Hader. So least significant difference of the LSD test is no correction. It sort of looks like you're doing a post-hoc, but it's actually just running every possible T test, which is a lot faster than programming each one in T.test. Right. But it's the same thing as doing all pairwise T tests with no correction, but we're going to use it as a comparison for our little chart. So this is I cannot pronounce that, an agriculture library, which has all of these programmed in it. And then you find a bunch of R documents where psych people are asking, has anybody programmed these? And I'm like, why doesn't CHEFE exist? But they did. So go ahead and install that library, or package, whatever we want to call it today.
I used to call it agricultural.
Yeah? That just seems weird. Lie. Yeah, but is that agricultures? I don't know. It's actually a really cool package. There's a ton of neat stuff in it, like skew, kurtosis, histograms. I think it was programmed maybe for a class or somebody's research lab, and they just programmed everything they needed. All right, so I got it installed. Now I'm going to load it up. And what we're talking about are all of these lines. And so I put out on the end which one it is. I mean, it's pretty obvious when it says SNK that it's SNK, but HSD is Tukey. So the first one we're going to run is LSD. Okay. And we're doing this on the output. So this is why you have to save the ANOVA. So it runs the post-hoc test on that output data. Comma, the second word on this is the IV. So when we get into having multiple IVs, this will let you run each IV separately. Super nice. Group equals false turns off all the means and stuff, so you can either turn that on and not see P, or you turn it off and see the P value. Console equals true gives you the information you need. So those two are specifically so we can see what the P values are. Okay. And so this is no correction. This is a least significant difference test, which is T, and no fixes. So let's run that. It's a really pretty chart. It gives you a bunch of stuff at the top. So it gives you mean squared error, and that's from what it's going to use as the denominator for each T test. It tells you the critical value of T and the degrees of freedom for T. So that's like the 0.05 cutoff, given this correction. So we don't have any correction right now, so that's the one for 12. It gives me the mean here. So here's the little Lido mean for each group, the standard deviation. That should be N. I don't know why it's R, but that's how many people are in each group. Lower confidence interval, upper confidence interval, and the min and max is beautiful. It's such a nice piece of output. Yeah. And then this is the important part down here. So this is where the actual magic happens. So I have here. So just like the output in SPSS, it does not actually give you T, which is kind of annoying. So that's the only bad part about this output. It tells me the mean difference. So this difference here is just this one subtracted from that one. It gives me the p-value for that difference and the little stars, whether or not it's significant. So most people would say this is marginal because it's less than 10. And then the confidence interval of the difference. It does not give you T, though. So when you report post-hoc tests, often what you're saying is group 1 is different from group 2, and then you'll do P. And then some form of Cohen's D or G. But to get the numbers for Cohen's D, you could run T apply, or you have that output right here. Right, so you can use the means and the standard deviation and N. Yes, you will have to do it 3 times. There's no magic cure-all for having to calculate effect size for multiple comparisons. I wish there were. My life would be better too. Okay, so are these significant? Well, the high dose versus the low dose is not. Right, it's marginal, it's 0.07. High dose versus the placebo is. So people who are getting the high dose of Viagra have a higher libido score, and then the low dose versus the placebo is not. So we kind of get this stair-step effect. The only one that's different is high versus none. So on our little comparison chart here, we're going to list the mean differences. So I got none versus low. Let's do that one first. None versus high. And high versus low. So I'm just filling in this chart. So, it did them in reverse order. So high versus low, the mean difference is 1.8 points. High versus none, 2.8. And 1, right? Yeah. Okay, so that's just the mean difference. So what's happening is it's comparing if this mean minus mean is different than chance, than 0. Now our p-value for least significant difference, which is no correction, because it's just fun to write LSD. You wouldn't write that in a paper. You would say that you did a t-test with no correction. You could, but people would think that you were, I guess, an older researcher, because that's sort of the older term for it. Okay. So we got 0.065, 0.008, and 282. And what we're going to do is compare these p-values to corrected p-values. So that is no difference. No correction. Now, Bonferroni is probably the most popular, other than 2V, because it's so simple. And so this falls under contrast or restricted sets of contrast. So there's a group of post-hocs, there's still post-hoc tests, or corrections, that sort of fall under, like, if you only have a small number of comparisons, so a restricted set of things you want to do. And that means that they're more powerful when there are less comparisons. Okay. So Bonferroni is super popular. Okay. So as I add more groups, Bonferroni becomes too restrictive. People don't like it. Okay. So when it's restrictive, that means your type 2 error goes up. It's harder to find a significant difference. So what you want to do is have a nice balance of correction and being able to still find effects. So test with smaller numbers of families, so less numbers of groups. And what that does is it adjusts the p-value. So Bonferroni adjusts on alpha rather. So instead of setting alpha to 0.05, we're going to reduce alpha. So through some fancy math, some Monte Carlos, we've shown that the family-wise error rate, so that's alpha, is less than the number of comparisons times alpha. Okay. So alpha family-wise 0.05 is less than that 1 minus alpha to the c. Okay. So that's bad, because then for each comparison, alpha is getting bigger and bigger. Right? So for 3 comparisons, alpha is 0.14. Okay. So what do? We just divide alpha up by comparisons. That's why people like it. It's really simple. Take 0.05 and you divide it by the number of comparisons you're doing, new alpha. So if I have 3 comparisons, my new p-value I'd have to look for is 0.01677666666 forever. Because 0.05 divided by 3. So this would still be significant and the other 2 would not. So it doesn't really change our results here. People don't like Bonferroni because it overcorrects for a large number of tests. And the more tests you have, the more restrictive it gets. So some other options are Sidak Bonferroni, and there's about actually 10 in R that I was reading about but haven't heard of before. And then Dunnett's test, which most people don't recommend. So Dunnett's test is, I think you have to have a real control group. And so Dunnett's test doesn't work all the time. But those are some other options that you can't do. But instead of doing all of that myself, dividing and then remembering what the score is and then trying to explain to people this P is significant and this P isn't significant, I'm just going to run the Bonferroni line. So the next line down is the LSD test, but it's got this actual p-adjust out here. So p-adjust means adjust the p-value based on a new criteria. So instead of it being 0.05, adjust p for Bonferroni. So it counts up the number of tests that you're doing and divides by that. And it says, okay, if I now use 0.02 as my alpha, what is my found p? So the way that works, here's our normal test. We find 5%. And we come up with a cutoff score. So it might be 2.17. We talked about the magic mystery machine. It's got to go to either side. If you decide that, yeah? Question?
Should the none and low and the high and low be switched?
None.
The values?
Maybe.
For LSD?
Oh, likely. Yes. Right, that makes more sense. Sure. Did I do it wrong? Low dose, placebo. Yes, thank you. Okay, where was that? Oh, we come up with a cutoff score where it's 5%. If we decide to say alpha shouldn't be 5%, it should instead be 0.016666%. Essentially, we now have to move those cutoff scores further out, where this adds up to 0.016%, which divided by 2 is 0.008, I guess. Ish. Or it adds up to 0.05 divided by 3. So that means the cutoff score gets higher. I'm making up random numbers, by the way. So that means our car has to go further. So that we've moved the finish line. You're basically picking up the finish line and moving it further away. And so what that means is when I calculate exact P, so remember the P values you get from these when we run the statistical test is the probability of the null of this experiment happening if the null is true. So it's like this one study. So what it does is it takes how would I have gotten this result based on my new cutoff score. So you don't see the adjustment as actually part of the cutoff. It just changes what the exact P would have been by changing alpha. That kind of makes sense to people? The end game is always the same. It's changing the p-value, the probability of these results given the null is true. But the way it adjusts the p-value is different. Okay, so this one adjusts alpha. The other ones adjust other numbers, but the end game is all the same. It adjusts the exact p that you get. So let's see that in action. So I'm going to run my Bonferroni. And it says right here, p-value adjustment, it's Bonferroni, which is how I checked if I was spelling it correctly, because I never remember if it's 2 R's or 2 N's. Sometimes I just add extra R's and N's to cover myself. Oh, I got pretty close. 2.78. I guessed it was 2.83. Right? So look, it moved the t value. So when I ran the LSD, it was 2.18. Now the critical value is 2.78. So we've moved the finish line further away, which changes our p-values. And you'll see by quite a lot. Let me see if I can get them in the right place this time. High versus low is 0.20 now. If I round up. High versus placebo is 0.025. And then low versus placebo is 0.845. So it's adjusting alpha, our 0.05 rule, but that affects the end p-value. And so you can see Bonferroni is pretty restrictive. I mean, look how much it's changing some of these probabilities on the same numbers. So that's one reason why people don't like Bonferroni. I mean, it's easy. It's easy to run. And if you didn't have R and you just had the p-values, you could do it by hand. So it's popular, but it's fairly restrictive. Okay. And so what we will cover in lab to finish the section, student Newman-Cools, Tukey. Tukey is the most popular correction. It's not Turkey, I know. It'll be better, but it's Tukey. It's a dude. Was a dude. And then Shefe. So we'll cover 3 other types. But if you're looking at the code here, they're very easy to run. And so my one quick, before we end, what we're doing right now is just to show you how all of these tests work. When you're actually running this on your own data and not for a class assignment, you would only do one. You would not run a bunch of post-hocs. So you only run one post-hoc. You can pick your favorite. Most people pick Tukey. But this is for demonstration. So that's why I have the little note in here, don't do all 5. You would only do one. I'm just trying to show you how they work. Okay. All right, so we will finish this in lab. It's not too many more slides, I don't think. Yay. And I will fix the notes right now and upload those so they have G-Power in them. Okay, so we finished with Bonferroni, and we're talking about how do they correct. So corrects on alpha. Now let's talk about a different type of set of tests, which would be SNK. So SNK stands for Student Newman-Cools. For a long time, it was just a Newman-Cools correction, and then they fixed it. So it's Student Newman-Cools. There are a couple of other tests that are more alphabet soupy. But what SNK and Tukey do is they're pairwise, they're technically called pairwise comparison corrections. And that's when you want to compare everything to everything else. So with Bonferroni, you could actually only pick 4. So if you had 10 comparisons, you're like, I just want to do these 4, I'm only going to correct for these 4. So you have that choice. And if you do that, you have to kind of do it by hand. But SNK and Tukey are really for correcting for every possible pairwise combination. Okay. Now this one's a little bit of a weird one. So what it does is it adjusts on the mean difference. So it comes up with a new mean difference. Okay. Which that, in a sense, adjusts the p. So the way that they adjust is different for each one, but in the end game, it always affects what is my p-value. But it adjusts the mean differences that are allowed, so the greatest mean difference in a step-down procedure. So it picks the largest mean difference first, so that's why we have mean differences written up here, and compares and gives it the most strict criterion. So it orders them. So it would do this, none to high, low to high, and none to low. And sorts them out by mean difference. And the largest mean difference is compared with the strictest criterion, and then the next mean difference down gets a less strict criterion, and then the next one down is a less strict criterion, hence the step down part of this. So it does give you more power for smaller mean differences. So you'll see we have better p-values for these 2 than Bonferroni. However, some people consider that cheating. So they say that increases the type 1 error rate at the bottom because you're getting more power as you go. So when you have more power, you have more type 1 error also. It's not as popular as it used to be because it was really, I think, designed for this kind of design, actually, where you had a placebo, a low, and a high, and you want the largest difference to be between none and high, and then this one and this one, so it made sense to step down. Now, a lot of our designs aren't this sort of experimental versus control designs, so step down doesn't make a whole lot, doesn't make sense. But what will happen when you run it, so it's got that exact same format. So the cool thing about this library, or this package, is that all of these stay the same, except for Bonferroni out here. And you just change what happens on the front. Okay. So SNK is for SNK. If you run that, it still gives you the means, standard deviation. Remember, R is N. Okay. And then this critical range. So let me go back to PowerPoint. It's a little bigger. So the critical range is the new mean cutoff. So the largest one, the third largest mean difference, is kind of the way it thinks about it, is the 2.8. So it's getting compared to 2.36. Right? So this high dose versus placebo is 2.8. It's being compared to 2.36. So it's significant. The next largest one is 1.8. It's being compared to 1.93, so it's not significant. Okay, so you can kind of see where it's getting its criteria from, but it's close, so that's why it's 0.06. Okay. And the last one is always compared to the second to last step down because of math reasons. So it's compared to 1.93, and it's not significant because it's only 1. And so the p-values are going to be kind of look like they're uncorrected because it's not a very stringent test, right? So it does correct, but not a whole lot. So let's see, we got 0.021 and then 0.065. So check it out here. It's basically uncorrected here. Okay. And then 0.281. Right. So the correction on the lower end is almost the same as not doing a correction. Now the correction on the highest one is more stringent. Okay. So that's why people like S and K, is because it gives you more power for smaller mean differences. But that doesn't affect the effect size. So if you're finding significant differences on the small end and the effect size is small, it's going to be hard to convince people they should care. Now, Tukey is the most popular. Plus, it's just fun to say. So, Tukey is HSD, so honestly significant difference. Most people don't call it Tukey HSD, they just drop it, they just say Tukey. There's actually several versions of Tukey. If you've ever used SPSS, there's also a Tukey B. Nobody uses that one anymore. But it is the most popular way to correct. And because it's sort of in the middle of the road, it's more stringent than S and K, less stringent than Bonferroni and Sheffe, so it's kind of like I'm going to even out the difference between being correcting and not being too strict. There's a couple of other types. There's Fisher-Hayter. I wish Fisher-Hayter were more popular because it's actually kind of like Tukey's nice cousin, I guess. This is even a little less stringent, but you have to do it by hand. You can do it in SPSS. But I couldn't find a good way to do it in OR that didn't involve like 10 lines of code. So, and then the Ryan, Enoch, Gabriel, Welch Q, which you have to have a computer do. I'm not even sure how it works math-wise. Everywhere I've ever read, it's like the computer does it. I'm like, somebody somewhere knows the math. And I think it's a variation on S and K. Okay, so Fisher-Hayter is like the variation on Tukey. REGW is a variation on S and K. And so I kind of went with the ones we could run fairly easily, especially because most people, after they learn this, go, I'm going to just keep doing Tukey. So Tukey's code is HSD. And it looks exactly the same, so you just change S and K to HSD. And that gives me middle of the road p-values, so 0.021. So at the topmost comparison, the largest comparison, Tukey and S and K are almost the same. But this is where they start to be different. So we got 0.147, 0.517. Well, that's why I said it's the middle of the road. So S and K basically is no correction here, and then Bonferroni is more strict, so this is the middle of the road. And this is essentially no correction. Bonferroni is very strict, and so that's where we're getting the middle of the road comment. Okay. On all of these, you would only do one, but we're doing all of them just so you can see kind of what they're doing, how they're correcting. Okay. And Tukey works the same way out here. So it's the same mean difference to p-value thing. We're not going to talk about how to actually look up what they're calculating for Tukey. So if you look here, it says critical range of studentized value, critical value of studentized range. That is called the Q statistic. That is not the mean difference. So S and K shows you the mean difference, but clearly that number is not the mean difference, or none of them would be significant because none of them are over 3.77. That is the Q statistic. When we get to repeated measures, if we can figure out how to do it without looking up Q tables, we'll go with that path. But if we can't avoid the Q tables, then we'll talk about how that's calculated. Okay. I would like to avoid Q tables if we can, because then it'll be just easier on everyone's brain. But we'll see when we get to repeated measures, I think next week. Or we might do 2 ANOVAs next week, I can't remember. We'll do our repeated measures at some point. But just a warning, this is not the mean listed here. Okay, all right. And then the last set of tests are technically what post-hocs are called. Okay. We kind of use post-hoc to mean all of these, right? The test is still independent T, right? These are all still corrections. But chef A is the most popular, and it's actually spelled with an accent, but I'll just butcher the poor man's name. And it's used to control alpha experiment-wise. Right, so remember, family-wise is within each hypothesis, experiment-wise is across everything. So it is probably the strictest one. And it controls for every possible combination. So all pairwise combinations and all complex combinations. So a complex combination might be, I'm comparing the control group, the none group, to an average of low and high. Okay. Or the high group to an average of none and low. Okay. So complex comparisons allow you to sort of average groups together. Over just the number of pairwise comparisons. Okay. So Bonferroni here is how many comparisons do you want to do, and that's what it controls for. SNK and Tukey is every possible pairwise combination, so that usually is more than Bonferroni. Chef A is every possible combination ever, so we're getting more strict as we go. And what that does is it corrects on F. So the F cutoff, which then changes the p-value. Okay. So all of these are changing p in different ways. So this one, the test is actually an ANOVA. So with LSD, Bonferroni, SNK, and Tukey, the test is an independent t-test. With Chef A, it's a one-way between subjects ANOVA with 2 groups, okay, which is the same thing mathematically as an independent t, but I think it helps to know that that test is an ANOVA, so it's correcting the F score for you. And that's the thing where we talked about it picks up the finish line and moves it further out. So it's taking your critical F value and moving it further away. Okay. And usually like we're talking like the next state is a very strict test. All right. Which I guess living here doesn't mean much since there are 3 states right away, but imagine if we lived, I don't know, in Washington or something. So it gives me my new critical value of F. So you can see that it's correcting on F. Okay. So it runs a couple of little ANOVAs. It doesn't show you the ANOVA math. It just shows you the output, so P. We got 0.026, so it's still significant. 0.170, 0.546. All right, 7. Now, it doesn't look that different from Tukey, but on the homework, I have you do one where there are 5 groups, so there are a lot more possible combinations, and you'll see that Chef A is very strict. Okay. You won't be doing all possible combinations because there will be 10 different tests. You're just going to look at 2 of them, but you'll see that there's a larger difference as you get to be having more options. These correct in very different ways. Okay. With only 3 groups, the correction's not that strong because there's only 3 possible combinations. Okay. But as you add more groups, Tukey and SNK will kind of continue to be middle of the road, and Bonferroni and Chef A will be very strict. Okay, before we get to trend, questions on post-hocs? All right. So the other option. So it wouldn't be, I would do all these post-hocs and a trend analysis. Normally you would just do the trend analysis. The trend analysis is really regression. And this is where you have categorical groups that have sort of this continuous layout. So none to low to high is a mildly continuous variable. I just broke it into groups. And I can test for if there's a trend, rather than testing if there are differences between groups. So this would tell me that it goes from low, none, and then low is higher, and then high is the highest, without having to do all these pairwise combinations. So some people like trend because it's just easier to explain. Like there's a linear trend. It goes from up across the board. So linear is clearly a trend. I don't have that on here, but linear would just be your normal straight line regression. Quadratic would be x squared, so you get the U shape. A cubic trend has to have 2 bends. So something like that, or more likely like this. And a quartic trend has to have 3 bends. So it would kind of go down and then up and then maybe up and down again. So that's x squared, x cubed, and x to the 4th. That's what it tests. However, if I only have 3 levels, it will only test my possible options for 3 levels. So if you have 3 groups, it's n-1 is the degrees of freedom, right? So it'll only test a linear trend and a quadratic trend, because there's no way to have 2 changes of directions with 3 groups. Like, it can only change directions once. And so if you have 5 groups, then it could test a quartic trend. Okay, so it will sort of automatically decide that for you. And by automatic, you have to put in the number, but it will decide based on the number of levels what to run. So I can't have a quartic trend with this because I just don't have enough time points to measure that. Okay, so you have to have at least 3 time points to get a quadratic picture. If that doesn't make sense, think about it this way. If I have 2 time points, there's no way to tell if that's a curve. Right? The only option is it's going to connect the dots. But if I have 3 time points, then I can tell, wait, maybe that's a curve. So you have to have at least 3 to test for this. And so this would be a really great option if your linearity plot looks all crazy. So if it is linear in the middle, but the edges are curving out, try testing one of these trends. And then on the example that's on YouTube, it worked out really beautifully. It was kind of an accident, actually, but the linearity plot is like, oh, God, I don't know about this. And then the trend worked out perfectly. So if you want to watch that, that'll give you an idea of like when trend analysis is really appropriate. Okay. All right, so my word of warning that I did not discover until I worked the homework last night is that for trend analysis, you have to make sure your groups are in the right order. So let me kind of show you what I mean by giving you an example of the homework. Because I actually had to like stop what I was doing and figure out how to fix it. So on the homework, you're going to have 5 groups: novice, psych students, intermediate, advanced, postgraduate, and therapists. And so that clearly has kind of an order to it. Like novices are not supposed to be next to therapists. But remember that R imports the data and automatically sticks them in alphabetical order, because it assumes that you want them in alphabetical order. And so if you did that and let it stay in alphabetical order, it's going to base that trend on them being in alphabetical order, which is not what you want. So you want to make sure that your levels are in the order that you would want them to test the trend for, which would be none to low to high, which is not in alphabetical order, right? So we want to make sure our factors were in the right order before we did a trend. So how do I do that? And that's actually something you already know, but you didn't realize you knew it. So what you do, and I think they're actually already in the right order, but we're going to just show you how you'd fix it if they weren't in the right order, is you would use the factor command. So I would do, so it's called data set in this example, so data set. $, dose is our categorical variable, equals factor. So we're familiar with doing this. We've done levels to factors, but now you're only just going to have levels. So it's going to be the data, the column name, comma, just levels. And you put them in the order you want. So I'm going to do a table real quick. Oops, I'm gonna type it wrong. Ugh. Dear me, wrong column. Okay, so this is how they're labeled currently. So I need to make sure I use the exact way they're labeled or it will wipe them out, which we've all done at least once. Okay. So let's say I wanted to put them in the wrong order. So let's say I didn't want to do placebo first, I want to do low dose for some reason. Okay, so I'll do low dose. And this is how you can tell if they're in the right order too. So I ran the table command and they're in the right order right now. But if I wanted to switch them around, and that's it. So there's no labels function because I'm not relabeling them. I'm just reordering them. Does that make sense to you? So I'm not transferring the numbers to words or the words to better spellings of the words. I'm just reordering. So if I ran that and then did a table, you'll see now they're in a different order. So you can use the table command to see what order they're in and fix the order that you want. And so I would tell you to do that at the beginning before you data screen or any of that stuff. It's sort of like a fixed accuracy. It's not really an accuracy error because it's not wrong, it's just in the wrong order. And so I was making a graph last night. I was like, okay, how do I reorder this graph? And then I was like, wait, I did that trend analysis all sorts of wrong. So definitely before you do a trend analysis, make sure they're in the right order. So I'm going to fix mine real quick. But thankfully, it's a command that we've used. There. Okay, so they're in the right order. Cool. All I've done right here in the notes is just get my means and standard deviations. And I think I did that before I figured out how to do post-hoc tests, because it actually gives it to you as part of the post-hoc test. But kind of a reminder, here's how t-apply works again. But you actually get the numbers you need for effect size during this. Alrighty. Alright, so we talked about what type of trend. So the way a trend analysis works, here's a pretty picture. Okay. So linear, quadratic, cubic, quartic. Okay, so lots of changes. So there's 3 bends, or 3 curves, versus 2, 1, none. As we have to set up the data in a slightly different way. So what I'm going to do is have you set up K. You can actually just put it into the contrast.poly, but I think it helps if you separate it out. So K is the number of levels, and it's going to be really something we'll use a lot when we do regression. So remember, K is the number of levels. And then if I look at the code here, so I've set that to my number of groups, it's 3. And then I'm going to rewrite my dosage column to be a polynomial contrast. So this cont.poly means polynomial contrast. And all that means is we're setting this up to test cubic, quartic. Okay. So polynomial means x squared, x to the cube. And it's technically a type of contrast. Okay. So we're setting it up by using the contrast command. So we're contrasting this column, and we're doing a polynomial contrast with k number of levels. Okay. Now, that does change the variable to a different type of variable. So if you look over here in your environment window, it now has a whole bunch of other stuff going on because it's set it up to run that type of analysis. Okay, so that does overwrite your variable. In the example videos, I actually make myself a new variable if you don't want to overwrite it, or you can just rerun the first couple lines of code. But then literally this is the same ANOVA out that we did the other day. So when we run ANOVA, it's still y is approximately x, data equals data. So I'm just going to rerun that, okay, and then get my LM summary. So none of this down here has changed. This is the exact same output you saw before, because I haven't really run a different test. I've just told it to test it in a different way. Okay, it's the same data, but it's like test this as a trend rather than as differences between groups. So what it'll do is it won't show you residual, but that's down here, residual standard error. It shows me dose.L, that's linear, dose.Q is quadratic, dose.T I think is, no, cubic would be a C because it's spelled with a C. most days of the week. It actually gives you t this time. So these are your t values, testing if that's significant, and then it gives you p. So the way that you can write these up is using these numbers. I think I did it. Did I do it here? Yeah. So there was a significant linear trend. So I have my t value. That's 12 here. Where did that come from? Okay. The 12 is from 12 degrees of freedom right here. And then I took my t, as in Tom, 3.116. Okay. And then p equals 0.008. So there is a significant linear trend in the data. Okay. No quadratic trend. So that kind of makes sense. So the output's a little different. It does give you a t value to report, unlike all the post-hocs, which just give you p. All right. So last but not least, effect size on post-hocs, which probably should have gone before trend analysis, but at least it's in here. Okay. So since post-hocs are comparing. There's cheese today, right? So since post-hocs are comparing two groups, we're going to calculate Cohen's d or Hedges g. So you shouldn't. This is mote. You'll have to have the mean standard deviations in n. You can get them from t-apply, because I wrote this before I figured out how that post-hoc thing worked, or you can get them directly from the post-hoc, right? Because I would only calculate it once, even though we did like all these post-hocs. So I could use this right here. Which is the mean in the first column, the standard deviation in the second column, and n in the third column. Those are all the numbers you need. So it's kind of nice because it's right there to calculate in mote. And so you'll do that today, so I'm not going to go over how to do mote again. But so if you can't remember, we can go over it individually. But you would throw that into mote and calculate d. So yes, you have to do it 3 times. So you'll have 1 for each one. Okay. Which should be very close. So how would I report those results? Well, actually, we're not going to get t. So this is from an old set of notes where we could get t. So planned contrast, let's change that. So post-hoc analyses using a Tukey correction, if you want to. Revealed that having any dose of Viagra significantly increased libido compared to placebo, but having high dose did not significantly increase libido compared to low dose. Okay. So I would only have P and D. So I'd also probably want to talk about none to low, so that was not significant. So having a high dose, sorry, these are based on a different set of results. So high dose of Viagra significantly increased libido compared to placebo. Having a high dose does not increase over a low dose. The low dose was not significantly different from a placebo. Right. So our p-value would be 2.22. This one? Yeah, 0.52. And I'm going to make up a d-value. So totally made up. And I will upload this corrected version. So if I'm doing Tukey, it's going to be 0.021 here. Or basically 0.02. I can round up to 2 decimals. And then the other one is 0.15. So those numbers will now match what you have in your output here, and I'll upload that for you. And so that is just the post-hoc part. So you would slap that together with the F-test part, which was a couple slides ahead of this, about there was a significant difference in levels of libido based on type of dosage, and you have all your F statistics. And then now tell me what happened. So the first line really tells me something happened. And you're ready. You're like, suspense! And then it's what happened. So talk about each test individually, and they'll all have P and D or G values. Too many rhyming letters in this lecture. We got T, P, D, like all the rhyming letters. So then instead of writing every single mean and standard deviation, that's where you include the picture. Okay, so it's much easier to include a figure with the means and confidence intervals in it than having to list each mean and standard deviation separately. Okay. So if you don't include a picture, you have to type them in the paragraph. And then here's the pretty picture. Ooh, fancy. Okay. And so I have all of that code here at the end. You've seen bar graphs multiple times now. Every day, be installing things. GG is so huge. I did figure out the error in car that you'll get. It's not an error warning, is because car and memis have the same name for a function. So you'll get a warning anytime you have two packages open that have the same name for a function, because it's telling you which one it's going to use. So that's what that warning is, by the way. All right, so we've got all of our theme coding. What? Oh, no, I didn't. Thank you. It's the worst. Okay. Stat summary, which is creating the bars. Mean CL normal, which is creating the error bars. And then I've got my two X and Y labels. And then I've got my non-functional error bars, because I forget that you also have to install this one. Oop. Spelled correctly. That seems to be important. Okay. Third time's a charm, right? Graph. Now remember, we could change the Y limit as well. So on the homework, I tell you to be sure you change the Y limit. And so that is scale Y contiguous, and that's limits equal when you tell it upper and lower limits. Okay, we did that last week, I think.